I'm Leo, the session chair. We have 3 talks in this session. The first talk is on the impossibility of key agreements from quantum random oracles by Per Osterlin, Hao Zheng, Kai-Min Zheng, Shihun, Yao-Tin Lin, Muhammad Mahmoudi, and Yao-Tin will give a talk.
Okay, thanks for the introduction, and thanks for being here so early. And so today I'll be talking about on the impossibility of key agreements from quantum random oracles. And this is a joint work with Per Osterlin, Kai-Min Zheng, Hao Zheng, Shen Fu, and Muhammad Mahmoudi. And this is Yao-Tin Lin. And I'll start my PhD at Santa Barbara this year. Okay, so in the classical world, we can do lots of things with random oracles. It is one-way and collision resistant, and it basically gives us private key cryptography. But an interesting question is that, can we get key agreement or public key cryptography from random oracles? So a key agreement is a 2-party interactive protocol, where Alice and Bob's goal is to share a secret key against the eavesdroppers. So they'll start with their private local randomness, and they can exchange messages. And finally, they output their own keys. And we say a key agreement protocol is with perfect completeness if they always output the same key. And the seminal work of Impagliazzo and Rudish answers this question negatively. They prove that we cannot use random oracle to get key agreement. But here, the random oracle is the only assumption, or otherwise, we can get key agreements from Diffie-Hellman or stuff like that. And they prove it by constructing a polyquery attack for every key agreement. But what if we allow the parties to use quantum computation? But if we allow quantum communication, then the BBA-Default protocol would give us unconditional secure key agreements. So what if the communication is still classical? And we would like to ask the following question. Can quantum computation, a random oracle, and the classical communication together gives us key agreements? And the random oracle model was proposed by Bonnet et al. It is a regular random oracle model that can be queried and answered in superposition. So here's our main question. Can we obtain a quantum version of Impagliazzo-Rudish result? And Hoso Yamada and Yamakawa ask the following question. Does there exist a key agreement where Alice and Bob can only do classical communication, but they can perform local quantum computation and make quantum queries to a random oracle? But every eavesdropper would need a super polynomial number of queries to find the key. And actually, we do not know the answer, but we have conditional results. So here's an overview of our results. So first, when Alice is classical and Bob is quantum, we construct an order D² query attack on every key agreement in the quantum random oracle model. And next, when they are both quantum, we propose a parameterized conjecture, which would imply a polyquery attack. And we're able to prove that conjecture with worth parameter, which would imply an exponential query attack. And finally, we also have a better result. So we found that if the Aronson-Ambanis conjecture is false, then there do exist a key agreement with imperfect completeness that is secure against classical eavesdropper. And notice that if we break key agreement in a quantum random oracle model with polyqueries, then it will imply the fully black box separations. So here's the plan. So first, I will introduce the notion of black box construction and reduction. And then I will review an attack in a classical case. And finally, I will tell you our result in detail. So after years of research and hard work, it seems very hard to construct key agreement from one-way functions. So can we instead prove the impossibility of doing so? But to prove unconditional impossibility, we have to prove first, one-way functions exist, which is also very hard to do it. And we have to prove key agreement does not exist, but they seems to exist. So we have to restrict ourselves to some general and interesting enough framework. So if we can obtain separation result in that framework, they are still useful and meaningful. And a definition of black box reduction was first formalized by Reingold, Trevisan, and Betham. So in cryptography, most of the time, the construction and reduction are black box. So suppose I want to construct a primitive P, say it's a key agreement, by using another primitive Q, such as a one-way function. Then in your construction of the key agreement, you don't really care about the code of the one-way function. You only care about the input-output behavior of it. That is, you only treat it as a black box or as an oracle. And as long as this bug is hard to invert, your construction of the key agreement should always work. And similarly, the reduction can only use the adversary as a black box as well. And however, the implementation of the one-way function and the adversary of the key agreement could be inefficient, since they are only given as oracles, and we only care about the number of queries. And the first quantum black box separation result was obtained by Yamada and Yamakawa, where they proved that one-way permutation and trapdoor permutation does not give you collision-resistant hash function in a black box way, even in a quantum setting. And in a quantum setting, the implementation now could have quantum computation power, and they can make quantum queries to the oracle. And then I'll review an attack on every key agreement with perfect completeness in the random oracle model. And this is called the heavy query learning attack, which was based on the work of Barak and Mahmoudi. So suppose Alice and Bob just finished the protocol, and Eve now sees the transcript. And she will first initialize an empty list L, which is a partial function. And then she will compute the distribution over Alice's view in her head. And here, Alice's view consists of her randomness, the transcript, and the set of query answer pairs that she learned from the random oracle. And we'll denote it by PA. And we'll use QA to denote the domain of PA. And we will call it the query set of Alice. So whenever there's a point that is with at least epsilon probability of being queried by Alice, but not yet in the list, if we'll go ahead and query that point to a random oracle and get the answer, and she will update the list by appending this query answer pair to it. And she will repeat this procedure until there's no such point. So Eve's strategy is quite simple. She just keeps asking valuable queries. So when she stops, she will obtain a distribution over Alice's view, such that for every point outside of the list, they are all unlikely to be queried by Alice. And then she will sample a fake view for Alice and output the corresponding key. And we can show that Eve's query complexity would be order D over epsilon. So with the proper choice of epsilon, Eve's attack will be efficient. And also, with high probability, Alice's query set in the fake view and Bob's query set in the real execution will be disjoint outside of QL. So this means PA prime, PB, and L are consistent with each other. So that means Alice's fake view will be consistent with Bob's view. So by perfect completeness, Eve will find Alice's key. And it is really tempting to generalize our attack into a quantum setting, but there are some technical issues. So first, there are no more well-defined query sets for Alice and Bob, because now they can make quantum queries. And when they proceed their computation, their quantum state change. So you cannot really talk about which points are queried and which are not. They are not random variables. And next, since quantum algorithms do not have random tapes, is inherently random, so it is not clear how you can condition on something and inversely sample someone's view. But the heavy query learning attack crucially relies on them. So is there a chance of extending the attack into a quantum setting? And here's our first result. We can break every key agreement protocol with perfect completeness, where Alice is classical and Bob is quantum. And Eve's query complexity would be order D squared. And in fact, the attack is the same, but the analysis is different. So since Alice is still classical, we can still talk about her query set, and we can inversely sample her view. And our proof was inspired by Zandri's compressed oracle technique. And here's an overview. So we'll first augment an additional oracle register that starts from uniform superposition in the computational basis, which is the 0 in the Fourier basis. And then we will delay the sampling of the oracle and keep it in superposition. And next, we will view the oracle in the Fourier basis. Then magic will happen. It will somehow record the queries made by the algorithm. So in a computational basis, the oracle register is truth table. But when we flip it around and view it in the Fourier basis, it will become database. And by the size of D, we mean the number of non-zero entries in D. So there's an important observation. The final state of any D query algorithm will be of the following form. So here, W means the algorithm's register, and H is the oracle register. But the content of the oracle register will be databases of size at most D. And furthermore, by deferred measurement principle, all Alice's and Bob's internal measurement can be deferred to the end. So given a transcript and the list, we can define a purified view of the protocol. And this is a pure quantum state. And I'll define it in the following operational way. So first, we'll run the protocol in superposition from scratch and without doing any measurement. And then the purified view will be the post-measurement state corresponding to TL. So this will be a quantum state with a bunch of registers. And here A and B are Alice and Bob's register. And HQL means the oracle register corresponding to QL. And the H negate QL means the oracle register corresponding to the complement of QL. And it also has a transcript register. And without loss of generality, we can assume Bob measured all his qubits at the end. So the measurement outcome B and the transcript T can be seen as the view of Bob, because they are all the information that Bob can learn during the protocol. So for every possible outcome A and B, we will consider the following state. And this state is obtained by fixing A and B in the purified view and leaving only the oracle register. And this state is important because by measuring this state in the computational basis, it will give you the oracles that are possible to generate the outcomes A and B, as well as the transcript T. And at the same time, they are consistent with the list L. And we'll let D max to be the database that has the most non-zero entries in this state. And this will be the quantum analog of the query set, QA union QB minus QL. So in a similar spirit, if Alice's query set in the fake view and Dmax are disjoint, then we can show that there will exist a full oracle that is consistent with the real execution and Alice's fake view. So again, by perfect completeness, if we'll find Alice's key. And we also have a remark. Because key ETL construct a simpler attack on key agreements with perfect completeness. But so far, we do not know whether their attack can be generalized to this setting. And next, here's our second result. We can conditionally break every key agreement with perfect completeness when Alice and Bob are both quantum. So in particular, we propose a parameterized conjecture about low degree and the low influence polynomials, and it will imply a polyquery attack. And here's how we define a quantum heavy query. So intuitively, the 0 in the Fourier basis somehow reflects the algorithm's ignorance on that entry, because the Fourier 0 is uniformly random in a computational basis. So motivated by this, here's how we define a quantum epsilon heavy query. So for a purified view of the protocol, we say a point in the domain is a quantum epsilon heavy query if the following holds. So this means pi x is the projection onto the non-zero elements, which acts on the x entry of the database. So I will translate in words. So this means the probability of obtaining non-zero outcomes by measuring the x entry in the Fourier basis is at least epsilon. And then I will introduce our attack. So we'll assume the key is 1 bit, and it is fine for proving negative result. Because if Alice and Bob cannot even agree on a bit, then of course they cannot agree on a key. So here's if's attack. She will still initialize an empty list. And then whenever there's a quantum-heavy query that is not yet in the list, if we'll go ahead and query that point classically and get the answer. And then she will update the purified view by computing the description of the post-measurement state corresponding to this query answer pair. And when there is no such point, she will output the more likely key bit in the purified view. And we can show that if's query complexity would be order d over epsilon. And here's the conjecture that we relied on, and we call it the polynomial compatibility conjecture, or PCC for short. So we conjecture that there exists an inverse polynomial delta such that for any non-negative integer n and d, and the distributions f and g over multilinear polynomials, where each of them are of degree at most d, and with variables x1 up to xn, where each of them are either +1 or -1. And every polynomial is with unit L2 norm. And furthermore, the distribution f and g satisfy the low average influence condition. That is, for every coordinate I, the average influence are at most delta of d. And then there will exist functions f and g in the support and an argument x, such that f of x and g of x are both non-zero. And we can show that this would imply the success of our attack. And if it is true, if's query complexity would be poly d. But unfortunately, we can only prove this conjecture when the influences are exponentially small in d. So if's query complexity would be exponential in d. So here's our third result. We can break every key agreement with perfect completeness, where Alice and Bob are both quantum, and they both make a constant number of queries. And finally, since our attack only makes classical queries, we study whether we can extend our attack to the imperfect completeness case. But we have the following barrier result. So we found that if the famous Aronson and Barnes conjecture is false, then there do exist a key agreement with imperfect completeness against classical eavesdropper. And this means if we want to obtain the separations in the imperfect completeness case, then we have to either prove a conjecture, or we have to construct an attack that makes quantum queries. And here are the open problems. So first, of course, we want to prove or disapprove our conjecture. And perhaps a more interesting one is that, can we construct an attack that really uses quantum queries? So maybe we can prove the impossibility in the imperfect completeness case. And that's all of my talk. Thanks for your attention.
Time for question. If you have a question, please come to the microphones. Okay, I have one question. So this is the impossibility of key agreement from quantum random oracles, or maybe one function. So there are many classical impossibility results, like impossibility result of IBE from PKE, something like that. Does your technique extend to other setting,
Also, I don't really think about the case of IBE, but we do have to think about the case of non-interactive commitment, and we found that maybe we can extend our technique to that case. Yeah.
Other questions? We have much time for question. No? Okay, let's thanks the speaker again. The next talk is online talk. Okay, so the second talk is succinct classical verification of quantum computation by James Batsek, Yael Tarman-Kalai, Alex Lombardi, Fermi Ma, Giulio Malavolta, Vinod Vaikuntanasan, Thomas Vidic, Lisa Yang, and Alex will give a talk.
We'll start a few minutes early. That's the plan.
We can hear you.
Yes. You want me to start now?
Yep.
All right. Hey, everyone. Thanks for coming. Thanks for the introduction. I'll be presenting joint work with this very long list of excellent co-authors. So let's get started. So the setting for our work is that of verifiable computation. So in this setting, we have some form of computation, which we're representing here by the problem of deciding whether some string X is in some language L. And in our setting, we have a verifier who wants to delegate this computation to a prover. So the prover and verifier exchange some messages in an interactive protocol. And at the end of the protocol, the verifier is supposed to decide whether or not X is in L. And in order for such a proof system to be useful, what we're looking for is a protocol that makes verifying this property easier than deciding whether X is in L on your own, easier in some sense. So there are two basic properties that you always want to hold in such a setting. The first is completeness, which is that if the statement is true, if X is in L, and both parties are honest, the verifier should accept. And the second is soundness, which says that if the statement is false, if X is not in L, then no matter what efficient strategy the prover decides to use, they don't have to follow the protocol, no matter what they do, the verifier should almost always reject. They should accept only with negligible probability. So the soundness that we're talking about here is only computational. An unbounded prover might be able to cheat, but a bounded prover cannot. So this is the setting. And classically, this has been studied for a long time, starting from two very influential works of Killian and Macaulay. And they constructed what we now call succinct arguments for NP. So they showed that every NP language has a very efficient proof system in the sense that there is a protocol where the communication is polylog T, where T is the non-deterministic verification time for the language. And the protocol's verification time is again polylog T, and also some fixed polynomial in the input length, which is unavoidable because you need to at least read the input. So this is basically as efficient as you could hope for. And certainly not something that you could achieve for general NP languages with a statistically sound protocol, for example. So this is the classical setting. But today we're talking about something different. We're talking about classical verification for quantum computation. So here the notion of the verification being easier than computing is different from just the question of verification time, etc. Here, we're requiring that the verifier is entirely classical, even though deciding the language requires running a quantum computer. So in this model, the prover can run a quantum computer, the verifier cannot. And so in particular, the protocol transcript should be entirely classical, and the verification decision should be computable by a classical algorithm, efficient classical algorithm. So this is the setting for today. And this is a highly non-trivial problem, even in the case where you don't require any form of succinctness or time efficiency. So in a breakthrough work of Mahadev, it was shown that this is possible. Like that, in particular, assuming that the learning with errors problem is hard, even against quantum attacks, there is a protocol for classically verifying any efficient quantum computation. So given everything that I've said, you can imagine what the question is. The question is, can we get the best of both of the two efficiency guarantees that I just described? Can we get a succinct and easy to verify interactive protocol for arbitrary quantum computation? And the answer is that we show that you can. So in particular, we show that assuming that LWE is post-quantum, and additionally assuming the existence of indistinguishability obfuscation that is post-quantum, we build succinct arguments for all quantum computation. And the result is quite analogous to Killian-Macaulay. That is, for every language in the quantum Merlin-Arthur complexity class, which is the quantum analog of NP, you get a protocol where the communication is polylog T, where T is the analog of the non-deterministic verification time, and the protocol verification time is polylog T and input length. So basically exactly what you would want. So in a little more detail, to make sure I specify the result carefully enough, if the original computation is in BQP, so this is the quantum analog of P, we get exactly what I just said, where the prover is also efficient. The prover runs in BQP. When you generalize to QMA, the prover is also efficient, but only given some polynomial number of copies of the original witness state. And yeah, so a lot of protocols in the quantum setting have this drawback, and it's an interesting open question to understand whether this is necessary. So we have some auxiliary results in addition to this main result. So first of all, this QMA protocol can be made zero knowledge if you want. So in addition to all of the things that I've said, the verifier, even if they cheat, also still cannot learn anything at all about the QMA witness. Additionally, just sort of as a byproduct of how we construct them, the protocols can be made public coin. So the verifier sends just random strings in every round, except for the very first message of the protocol, which is private coin. And this means that we can also compress the protocol into a non-interactive protocol in the quantum random oracle model using the Fiat-Shamir heuristic. So this means that we get a succinct or a form of succinct non-interactive arguments for QMA, where like in the quantum random oracle model. So these are our main results. Before getting into them, I should mention one related work besides the original Mahadev construction. There is a result by Chia, Chung, and Yamakawa from TCC 2020, where they construct also a form of succinct non-interactive arguments for quantum computation, but they require a very long trusted setup phase that generates a long common reference string for the prover to use, along with a secret verification key for the verifier. And on top of that, they also make use of a hash function similar to the hash function we're using in our non-interactive protocol. But although you analyze security in the random oracle model in their protocol, even the honest parties, the prover and the verifier, actually use explicit code for the hash function H and violate the random oracle model's like underlying assumption. So this is a heuristic construction. So on the flip side, what we're able to do in this work is, first of all, by allowing interaction, we're able to construct a protocol in the plain model with no setup whatsoever. And then for the quote unquote non-interactive protocol, I say quote unquote because there's still a short trusted setup. But in the non-interactive protocol, we have only a succinct, efficient trusted setup, and then a random oracle hash function. So you might ask, well, what changed from 2 years ago? What's enabling us to get a better result? And there are a couple of like aspects to this, but the one I want to highlight here is that this prior work is making essentially generic usage of the original Mahadev non-succinct protocol, and they want to sort of generically convert it into a succinct protocol. And there seem to be some inherent limitations to what you can do if you take an approach like this. And on the flip side, what we do is we look very deep into this black box and we sort of prove things from scratch. And this enables us to get these better results. So I'll soon show you a little bit about our techniques. But before going there, let me mention two open problems that I think would be fun to solve. One is, do we need obfuscation? Can you rely on LWE alone? Of course, you could do that if you could build obfuscation from LWE, but let's leave that aside for a second. So in our paper, we managed to do this, that is avoid obfuscation, for the easier problem of batch verification, where the protocol is succinct only with respect to the number of instances that you're batching. But it's open to do this for general QMA or BQP computation. And the second open problem I want to mention is, can we get a protocol that is publicly verifiable? So and this is open even in the non-succinct setting. All the protocols that we know require the verifier keep some secret state that they need in order to make the decision at the end of the protocol. In our setting, it would be nice. It'd be nice to have a publicly verifiable protocol, because then you would get like a real succinct non-interactive argument or snark for QMA computation, which is something that I imagine you might want, and that would sort of complete the picture, saying that basically everything you can do in the classical setting, you can also do in the quantum setting. So here are two nice open problems. But for the rest of the talk, I'll give a sketch of just the main results. So just a succinct argument system for quantum computation. So in a little more detail, let me tell you what we do in this paper. The construction of our protocol can be broken up into two steps. In the first step, which is the main step, we build what I'm calling a Laconic verifier protocol. And by that, I just mean that the verifier to prover communication needs to be succinct, and we've imposed no further requirements besides this fact. So we build such a protocol from IO and LWE. This is the only place where obfuscation is actually used, and it's even more localized than that. It's used for a very specific purpose. It's used to come up with some sort of succinct representation for a large number of public keys, for some public key scheme. So we write down some primitive that we call succinct batch key sampling that's satisfies the properties that we need in order to make a security proof go through. And we can so we write down a definition and construction in the paper, and it's quite localized. Mostly this tool is plugged into a generic construction, and then we give a new security analysis for this generic construction of classically verifiable quantum computation that we think is pretty modular, and in particular, it generalizes immediately from the non-succinct to the non-laconic verifier to laconic verifier setting, and we hope the security analysis will be useful in other work on quantum verification. So this is the main bulk of what we do. The second part to the construction is that we write down a generic compiler that starts with a laconic verifier protocol, at least a public coin laconic verifier protocol, and produces a fully succinct argument system. And this uses as a tool a strong enough form of post-quantum succinct arguments for classical computation, which some recent work has constructed for us that suffices for what we need. So these are the two main steps. And I'll start by sketching the second step because it's easier. So let's think about the compilation step. So imagine that somehow you were able to construct a protocol where the verifier was laconic. So as described on the slide. And so right now let's just assume that the protocol is only 4 messages long. It doesn't really matter. Let's call alpha 1 and alpha 2 the potentially long messages that the prover sends to the verifier in the protocol. So we would like to convert this into a fully succinct protocol. What I'm about to describe is maybe the second thing you would think of rather than the first thing, but it's like a reasonably straightforward approach. So here's what you do. Every time the prover wants to send something that's long, instead, of course, send a hash of the message instead. So we'll start by running the first two messages of the Laconic verifier protocol, where the prover only sends the hash of its own message. Of course, now at this point, the verifier doesn't have enough information, or the verifier will not later have enough information to make a decision. So the verifier is going to need some help. So at this point, and it's crucial that we do this right now, the prover is also going to send a succinct argument of knowledge of its message alpha1, which means that more formally, they send an argument of knowledge of a hash inverse of the message that was sent to the verifier. And I'll explain briefly why it needs to happen right now, but you need to do it now. So only after you send this argument of knowledge, the verifier then sends the next message in the Laconic verifier protocol, and we do the same thing. The prover hashes its second message and sends another argument of knowledge. And then after this was done, after all of this has happened, then the prover sends a third argument of knowledge that they know, again, hash inverses of its own messages. In principle, these might be different hash inverses, but the collision resistance of the hash function will sort of constrain them to actually be the same hash inverse, but a priori they're potentially unrelated. And so the third argument of knowledge says that the prover knows two hash inverses that together compose a transcript that the verifier would accept along with the verifier's two messages. So this is the structure of at least one of the versions of our compiled succinct argument system. So why am I writing down a protocol with this structure as opposed to, say, like just including one succinct argument of knowledge at the end? The reason is that we need to, or we want to, reduce the security of this composed protocol to the security of the underlying Laconic verifier protocol, which means that in the reduction, we need to be able to produce the prover messages in an online fashion for the Laconic verifier protocol. We need to be able to produce alpha1 without knowing for like a full transcript of the protocol. And even more importantly, we need to be able to produce alpha1 without using the verifier's like internal randomness that might compromise the security of the protocol. And this third argument of knowledge at the bottom is implicitly using the verifier's internal randomness because the statement the verifier would accept requires this. But with this structure, there's a nice security reduction where we just sequentially extract alpha1 from the first protocol and then extract from the first subprotocol, extract alpha2 from the second. And that is how the security reduction works. It's how we break the Laconic verifier protocol given just a breaker for the composed protocol. And the fact that, like, in order to prove that this reduction works, you need actually a strong form of argument of knowledge where it's possible to extract these messages alpha1 and alpha2 without disturbing the internal quantum state of the adversary breaking this larger protocol. But conveniently, in a recent work with Fermi Ma and Nick Spooner, we showed how to build such a succinct argument system for NP, and so we can plug it in and we're happy. So that's all I want to say about step 2. So now let me just say a little bit about the Laconic verifier protocol. So skipping over quite a few details, the key step in constructing a quantum verification protocol following the blueprint of Mahadev is constructing what is called a measurement protocol. So this is a protocol where the prover starts with some L-qubit quantum state psi. The verifier starts with a string, an L-bit string H, which is a choice of bases. And the verifier wants the prover to measure its state psi in these bases where like an HI equals 0 means that the prover should measure that qubit in the standard basis. HI equals 1 means the prover should measure the ith qubit in the Hadamard basis. So the verifier wants the prover to make these measurements and to report to the verifier, ideally, what these measurement outcomes are. Of course, you want this to be done in a verifiable way. And in a little more detail, what that means or how it's done is that there is a cut and choose aspect to the protocol. So there are two verifier challenges, 0 and 1. When the challenge is 0, the verifier is performing some sort of spot check and is not actually obtaining an output, just deciding whether or not to accept the prover as being reasonable or not. And when b equals 1, the verifier actually obtains a measurement outcome, in the completeness case matching the measurement outcomes of the prover's initial state psi. And security says that as long as an adversary P star is passing this spot check b equals 0 challenge, then the distribution of outputs m the verifier gets when b equals 1 is computationally indistinguishable from the measurement outcomes of some L qubit state psi prime. Like the prover in principle might not start with any state on the face of it, but security says that there is some state such that what the verifier gets out is consistent with measuring psi in whatever basis the verifier wants. In particular, this state psi prime is independent of the basis h, and the indistinguishability should hold for every basis choice at once. So that's the kind of protocol that we want. Mahadev constructs a non-succinct such protocol. And the relevant piece of information for this talk is what the verifier's long first message actually looks like. So what it is the verifier sends L, so a large number of independent public keys for some trapdoor claw-free function family. Don't worry too much about what the exact primitive is, but what you should bear in mind is that the primitive has two modes. So there are two different ways of sampling a key. And the way that the verifier samples the key depends on its basis choice. So for each I, the ith public key is in mode H sub I. So this is the structure of the protocol. So we want a succinct, or at least a laconic verifier protocol. Laconic with respect to the parameter L. So we want like a sublinear and L communication. And so first of all, this only makes sense if there's some succinct representation for the string H, but let's suppose we have it. What we do in this work is we write down a way to give a succinct representation of L public keys. We call this primitive succinct batch key generation. We construct it from IO. And roughly the security property that you need is that given this succinct representation for many public keys, you need that each individual trapdoor claw-free function remains secure, even if all L-1 of the other ones are compromised. Say that you get the secret keys for all L-1 of the other ones. That's the sort of security property that you need. And so it's not too hard to write down a protocol. It's not too hard to syntactically write down a laconic verifier protocol using this idea. The tricky part is actually proving that the protocol is sound. In particular, soundness doesn't follow from a black box use of the Mahadev 18 result. So there have been a lot of works building on this original protocol, but almost all of them either use the protocol completely as a black box, or they say, okay, look at line 157 of the proof, and line 157 of the proof is still true in our setting, and so our protocol is also secure. So if we did that for this paper, we would our proof would be like a complete monstrosity, because our protocol is significantly different from the original protocol. And so instead of taking this approach, we write down what we think is a hopefully simpler, certainly more modular proof of soundness that we hope will be useful in other work that on quantum verification. And I'll just say a word on this soundness proof. So we start with and expand on an approach outlined by Vidic in some unpublished lecture notes called the operational qubits approach. We extend it to prove the strong form of security the measurement protocol that I just described is asking for. So the argument basically goes, suppose you have a cheating prover that's working. We want to find this L-qubit state psi prime that's consistent with what the verifier gets. But what we actually have is just the internal state of the prover. And note the prover may be cheating. The verifier may not be getting outputs that are just the measurements of the prover state psi in the standard or Hadamard basis. The prover doesn't have to behave in that way. But we find a psi prime nonetheless, and we do it as follows. We first identify 2L different ways of measuring the prover's state psi that we call pseudo-Pauli observables, such that when you measure the prover state with these observables instead of standard and Hadamard basis measurements, those measurements outcomes actually match what the verifier gets, the verifier's output. So what does it mean that these are pseudo-Pauli? I'm hand waving it here, but the point is that they should behave like standard and Hadamard basis measurements in the way that they commute and anti-commute, the way that they relate to each other. So in particular, you should have an uncertainty principle between the ith quote unquote or pseudo standard basis measurement and the ith pseudo Hadamard basis measurement. So that's like roughly speaking why they are like standard and Hadamard basis measurements. And given this, we then extract an actual state psi prime that is not the prover states, where like we convert pseudo polys to real polys. So we extract psi prime whose real measurements match the pseudo measurements of psi. And to actually implement this, there are 3 questions that you care about. What are these pseudo poly measurements? How do you find psi prime, and how do you show that it works? I unfortunately don't have time to explain it. I'll give like 1-sentence answers to each. The pseudo poly measurements you get by like pretty syntactically reading off how the prover responds in the protocol. And what's nice is that the relationships, the pseudo poly relations between these xi's and zi's and xi and zj you can sort of read off from the basic security properties of the Traptor-Clawfree function family, which is quite nice. Then how do you get psi prime? It's output by an extractor that pretends that these pseudo polys are real polys and teleports psi onto a new register, which is actually L qubits, and we treat that as the outputs, as the extracted state. So the point is that you can write down a circuit that does quantum teleportation in the event that the pseudo polys were real polys, as a circuit that uses poly x and poly z operators, and you can replace the poly x's and poly z's with the pseudo operators, and that is how the extractor works. Finally, the way you show that this state actually like satisfies the properties that you want is by giving a physical interpretation of what measuring this extracted state actually means in terms of the pseudo poly measurements. And I encourage you to look at the technical overview of our paper for an explanation for how all this works. So that's everything. Thanks for listening.
Thanks, Alex. We have time for one quick question. If you have a question, please come to the microphone.
Yeah, hi. Thank you for the talk. I was unclear about what you were proving in the argument of knowledge, which is you prove knowledge of the underlying thing alpha. So what is alpha? Is it just all the messages in the CBQC protocol?
Yeah. So for each message of the protocol with long prover messages, you have the prover hash that message and then prove knowledge of a hash inverse, which the first proof of knowledge is just I know some string that is a hash inverse of the message I just sent to you. Later in the third argument of knowledge, you actually tie that together with the original protocol. Like there you prove that you know hash inverses such that the verifier would accept the 4 message, like the transcripts composed of the verifier's own 2 short messages and the prover's long messages.
Thank you.
Let's thank the speaker again. The final talk of this session is on the feasibility of unclonable encryption and more by Pravanjan Anand, by Fatih Khalil, Shanjan Li, Chipen Liu, Mark Chandri, and Chipen is going to speak.
We do not see the slides.
No?
Could you see it? So could you help me? Okay, great.
They can see it.
The slides is shared, right? Also
It should be, yeah.
on Zoom, right?
Yeah, they
Okay.
can see them. Okay.
Okay, great. Okay, let's start it. So yeah, I'm Chipen Liu from Simon's Institute. So I will be talking about the work on the feasibility of unclonable encryption and more. This is a joint work with Prabanjan, Fatih, Xinjie, and Mark. So okay, let's.
Excuse me, I'm not seeing the slides.
Not seeing the slides. Yeah, could you help? Okay, thanks.
That works.
Okay. By the way, it's not working. I cannot go to the next slide. I don't know. Okay, anyway, I can use the keyboard. All right. All right. Okay, it's lost the focus. Okay. Okay, so let's start it. So the talk is basically about taking advantage of the most fundamental property of quantum information, which is the no cloning theorem. That says, if you don't know a piece of quantum information, there's no general quantum machine can copy the quantum state into two identical copies, so, which is impossible. So this unclonability of quantum information actually brought up the whole field, which I called unclonable cryptography. So here's a list of unclonable cryptography, and you're probably already familiar with most of them. The first one is the starting work, which is the quantum key distribution. And also there are a line of work, including quantum mining and quantum copy protection for a broad class of cryptography. And in this work, we will both basically consider the most fundamental unclonable crypto primitive, which is the unclonable encryption. So just like the one-time pad to the symmetric key crypto, which is a one-time symmetric key encryption, we also, in this talk, we will consider the one-time symmetric key unclonable encryption, which I will explain. So we believe it is the most fundamental and important thing we need to understand and to explore the whole area of unclonable cryptography. All right, so let's start by looking at what the definition is. So the definition was first introduced by Broadbent and Lord. So I mean, it's an encryption scheme. So what extra property it should satisfy? It is the which we call random message security, unclonability. That says, assume you have assume you have a random message and encrypt it as a encryption, and you give the encryption to adversary, which we call Alice, which is the adversary who doing the splitting attack. The Alice getting the encryption, splitting the message, the encryption into two quantum states. And later on, these two quantum states, which are handled by Bob and Charlie, who are non-communicating parties, who later receive the secret key, which is for them to recover the original message. And the unclonability guarantees that there's no way for both Bob and Charlie to independently recover the original message, even they're given the secret key. So the security guarantee says that the probability of this colluding adversary, Alice, Bob, and Charlie, they together independently recover the message m prime equals to m double prime equals to original message m. The probability will be super small. Let's say either negligible or sub-exponentially small. And in their work, they can show the probability can be either negligible or sub-exponentially small, either in the information theoretical way or in the idealized model, which is the quantum random oracle model. Okay, so that's the security called random message unclonability. Okay, but this is not the ideal security what we want. So here's the issue. So basically, this security doesn't guarantee Bob and Charlie to learn no information about the message. So for example, Bob and Charlie can both learn a single bit of the message, but still doesn't violate anything about this guarantee about the probability. So here, they identify the problem and propose the following definition, which we call it as CPA-style unclonability, just like when we define CPA security in the classical crypto. So in this setting, a pair of message, which are M0 and M1, are chosen by the adversary. So let's say chosen by Alice. And then the challenger will randomly pick one of the message and encrypt and give the encryption to Alice. And later on, Alice just do the same splitting attack and having two independent encryption register to both Bob and Charlie. And their outcome was to predict which message were encrypted under the original quantum ciphertext. All right. So the guarantee is the probability of both of them simultaneously guess the bit correctly should be very, very close to half. So that basically says there's no way you can split the quantum encryption into two encryptions. In other words, this quantum ciphertext can only go one of these two paths. In other words, it only goes to the upper path or going to the lower path. There's no way you can copy any meaningful information. All right, so that's the definition we call CPA unclonable, CPA style unclonability. All right, so and here's a special case, that is when the message only having length 1, then we don't need to let's say let Alice to choose the message. We can just focus on the case where M0 equals to 0 and M1 equals to 1, and that's the case we will consider in the work. All right, and I mean our work can extend the result to arbitrary n, but just for convenience, we focus on the length is meant to be 1. Right. So okay. So let's look at what happened in the previous work. So in Broadband Lord paper, they first show that it is possible to construct a scheme which satisfies random message security, just as we seeing either information theoretical way or in the random oracle model. And they identify the problem of the definition, and they propose a new definition, which is the optimum security or the CPA security, CPA unclonability. But they don't find a way to prove it. And later on, I mean, even in the quantum random oracle model. And later on, Magins, Schaffner, and Tamasby, they show that actually in the original construction by Broadband Lord, there's a technical barrier, that is using the proof technique in the Broadband Lord paper. There's no way you can show the scheme satisfy the optimum security. In other words, it seems like a dead end. So that's all we need about the this one-time symmetric key unclonable encryption. So in this work, we show that it is actually possible in the quantum random oracle model. So we basically give alternative construction, which is super close to the broadband LORD construction, but there's some caveat, and we give a new proof, and also we take advantage of our modification, and we can show that this object is actually exists in the quantum random oracle model. In other words, the most fundamental unclonable crypto it actually exists. Right. So that's the result. Okay. So and as I just talked about, this is our first result that says there's exists an unclonable encryption scheme with the optimum CP unclonability. And we also show other result. The first result is an impossibility result. That's says unclonable encryption cannot be both information theoretically secure and deterministic. Here, deterministic basically means the encryption and decryption procedure will be unitary. And this is a justification of our first result that says either random oracle model is necessary or our construction is also randomized. So the randomized structure is also needed. I mean, either the randomized structure or the random oracle model is necessary to achieve the optimum security. And also we show application to copy protection of point functions. This is not a black box reduction, but we basically borrow the proof technique from our first result, and we extend to copy protection for point function as our application. All right, so that's all the result, and let's move on to the somewhat technical part. So here's a roadmap. We will first record the construction in broadband and LORD work. And then we will see what's the challenge. So I will give you some attempt. And the attempt is, of course, failed because it's called attempt. And then I will show our construction and how we overcome this barrier. OK. So let's start by recalling the construction in their work. So we need to start with the quantum state, which I hope most of people are familiar with. But if you don't need to worry. So it is called the Wizner States. So so the Wizner state is a quantum state that encodes a classical message or classical string, which is the m bit x. So and basically given an x, we also have a theta. You can view it as like a secret key to encrypt the classical message. So given x and the classical theta, both are classical, you can generate a quantum state, which we call x theta. So and also the reverse is also efficient. That is, given the quantum state, you can extract the x from the quantum state. All right. So I don't want to explore about the structure, but there are like two fundamental property we will use in the construction and in the proof. So I call it unpredictability and unclonability. So let's see. So the first one is called unpredictability, which says given a quantum state, which is the BB84 state, but without giving an adversary the theta, there's no way to recover the message x. And the probability of a successful guess will be 2 to the minus n. In other words, if the adversary has no information about the basis then this x to the theta is completely hidden for the adversary. That's the first thing we will use in the proof. And the second property is called unclonability, which is will be heavily used in our construction. That says, given a random Wizner state, there's no way to do a splitting attack such that both can recover x. That is, the probability of the simultaneous guess such that x prime equals to x double prime x to the original equals to the original message is at most some exponentially small function. All right. So this is over random choices of x and theta. So you can already see from here how to construct a candidate of unclonable encryption, which you simply put your message as x and let your secret key to be theta. And this is very, very close to the broadband and Lord's first construction, the information theoretical construction. And they can indeed show that it is it has random message unclonability with roughly 0.85 to the n. All right. So, but however, if we construct in that way, there's no way you can expect the optimum security, the CPA style security, because this is the 2-bit case. We can simply look at the 2-bit case. So let this message to be M0 concatenating with M1. Oh, so here there are not 2 messages, it's just 2-bit. And we also should be aware of this Wizner States is actually bit-by-bit encryption. So you can simply getting this quantum state and split the quantum state into 2 registers. So what you did is, okay, you send the first qubit register to Bob, and you send the second qubit register to Charlie. And after receiving theta, they both can receive, they can recover M0 and M1. So in this case, there's no way you can expect CPA security, because you can simply choose M to be 00 or 11. So Bob and Charlie can always completely recover which messages are being encrypted. So it's completely violate what we want. So since there's no hope to just to directly work with this the game, so we ask the following question: can we reduce this CPA set unclonability to this random message unclonability, which we already know how to do, right? So for example, can we, based on an extractor, to extract a single bit and use the bit to do the encryption? Here is the attempt. So if we can prove a theorem statement like this, then we can have a unclonable encryption scheme satisfying the CPA secure unclonability. So here in the game, Bob and Charlie are not recovering the message, but they are recovering a bit. The bit is actually a extractor outcome on the random seed R and on the secret X. So if we can prove there's no way for Bob and Charlie to simultaneously get the outcome of the extractor, then we can build an encryption scheme like this. So the keys will be theta and R, which are the basis information and the seed for the extractor. And to encrypt, you simply output the BB84 state together with the message mask with the outcome of the extractor. And we know that there's no way you can predict simultaneously at least one of the message will be completely hidden. Okay, so but this construction, this road is actually difficult because there are basically 2 issues, but these 2 issues are kind of the same. So first of all, we are considering a non-local game. So the extractor should we should do like simultaneous extraction. So it's actually we don't know too much proof technique for this, and even worse, because these quantum states are generated by the adversary, so they can be arbitrarily correlated, it can be arbitrarily entangled. So it's even make this approach even worse. So and indeed, in Broadband and Lord's paper, they use extractor. So what they use is a random oracle. You can view a random oracle as the way to extract. So using this, the ideal extractor, they can show that their scheme satisfying random message unclonability with probability 9 times 2 to the minus n, which is much better than that without the random oracle. But still, it's far away from being implying the optimum security, because to achieve optimum security, you need this random message unclonability to have probability 2 to the minus n. So there's still a 9 gap, which there's no way to, we don't know how to fix. And later on, the Magins and Chris Schaffner and Tomasby, they show that the proof technique in this work cannot achieve the bound we want. So there's no hope to do that. Okay, so that's the barrier for extractor. So okay, so now let's look at how we handle this problem. So this is our construction. So to be honest, this is not exactly our construction. I cheated a little bit here. this construction is indeed the construction from Broadbent and Lord's paper. So, which is using using the random oracle as an extractor, and you produce 1 bit and to mask the message. Okay, but I will show how our proof technique can prove this by just doing a simple modification. So that's the construction. You have a BB84 state, you extract X from, you extract the binary outcome and you mask a message. And to decrypt, it's simple. You read out the X and you unmask the ciphertext and you can recover the message. All right, so this is the proof overview. So we will first show this CPA security, the CPA style unclonability can be reduced to a game we call identical reprogram game for Wizner States in the quantum random oracle model. And then this identical is actually pretty hard to deal with. And we reduce that, or we relate that to something called an independent reprogram game, which is much, much easier to handle. And finally, this game can be based on the unclonability, which we already know it's a property of the quantum state itself. And indeed, the reduction here does not quite work out. So we finally replace the quantum state with another collection of quantum state, and we can complete the whole reduction. So that's the overview. So let's start looking at the proof sketch. So that's the CPA, like how we define CPA style unclonability. That is, you are given a ciphertext, Alice trying to split, and then both theta are revealed to Bob and Charlie, and they try to recover. And the winning condition is set to be M equals to M prime equals to M double prime. So our first simplification is we remove the message here, and we, instead of recovering the message, now the Alice only gets the BB84 states or the Wizner state. And the goal is to recover the outcome on the hash function on the input X. So there's a very easy reduction. You can simply remove the message X, the message M easily. So that's well simplify this game. So we'll consider this game. If we can prove it, we prove the CPA unclonability. All right. So next, we have the observation that is this oracle given to Alice can be reprogrammed. So we define an oracle H prime, which is identical to H, except the evaluation on H prime, the evaluation of H prime on X is uniform. That is completely independent of H and of X. So why is that true? I want to say replacing this H prime, H with H prime doesn't change anything. So why is that true? Because we know that Alice won't be able to query H on X, or maybe he can, but she can only query a very negligible amount, because otherwise you can randomly measure Alice query and you can recover the X with high enough probability, which will violate this unpredictability of Wizner state. So that's how we use the first property of Wizner state. That is, we replace this H with H prime, and we completely unrelated this oracle with the other oracle given to Bob and Charlie. Okay, so what do we do next is we simply do a variable renaming. So we rename this oracle H by H prime B. That is, the H prime B will be the same as H prime, except H prime of X, which is the evaluation of X, is reprogrammed as B. So, they simply just rename, because H of X is also completely independent and uniformly random. So we just reprogram that as B. And the winning condition is set to be B equals to B prime equals to B double prime. So it just renamed it, okay? So that will make things easier. So then we can just look at the partial view instead of looking at the joint view of Bob and Charlie. So we know that if Bob can recover, can get B with enough probability, more than half, Here we only consider like one message, so random oracle only output a single bit. So if Bob can recover it with probability more than half, that means Bob must query this oracle HB prime on X with large fraction, with large weight. So in that case, we can add a random measurement over Bob to doing an extraction. So in other words, this random measurement simply just pick a random query of Bob and just completely measure it. And there will be inverse Pauli chance that the outcome is equal to B. Okay. And similarly, if Charlie has succeeding probability more than half, that means Charlie's outcome must be dependent of this B. So we can also add a random measurement and trying to catch the query Charlie made on X. And therefore, we also conclude that if the probability for Charlie is significantly more than half, then a random measurement will produce X prime equals to X with inverse Pauli chance. So it seems in that situation, we can both recover from Charlie or from Bob. But the question is, if we add random measurement to both Bob and Charlie, can we recover them simultaneously still with inverse polynomial chance? And if that is true, then we can break the unclonability of Wizner state, because we can simply construct a reduction which give X to the theta, and we can sample the hash function ourselves. And the reduction, I mean, we as the reduction can also do the reprogramming ourselves and trying to do the random measurement and the outcome and output X prime and X double prime. Okay, so but the approach has two issues. The first issue is how to reprogram H prime, because the point we want to reprogram is exactly the point we want to output, we want to guess. So we don't know. If we can reprogram at the first place, why we just don't output that? And the second issue is still the entanglement issue. That is because they're entangled, the measurement, this random measurement of Bob may completely destroy the behavior of Charlie. So there are some correlation. So maybe a successful extraction on Bob's side always imply a failed extraction or failed this outcome on the Charlie side. So there are two issues we want to solve.
You are running out of time, so
okay, sure. Let me quickly wrap up. Okay, so our solution is to, instead of looking at the identical, because in the previous game we reprogram using the same B, we're reprogramming using different B, and we realize that this independent reprogramming is very, very close to the identical reprogramming, and this is our main technical lemma. So this proof needs a very careful analyze in the corresponding Jordan block, which I will ignore, which may involve too many details. But I think this technical lemma will be useful for other independent versus dependent non-local games. So and that solves the first issue, which we reduced to a random independent reprogram game. And for the first issue, what we do is we simply we observe that reduction can only reprogram on if the adversary ever queries. So if the adversary never queries, we don't reprogram. Only if the adversary queries on the position we want to reprogram, then we do the reprogram. And this can be based on so-called the coset states, and which also satisfy all the property we want plus the verifiability, which is we can verify if this X is the point we want to reprogram. Okay, so this is our construction. We replace all the building block with the so-called coset states, and then we can complete the proof and showing the optimum security for unclonable encryption. So, and that's the recap of the proof. And since I don't have enough time, and that's everything I want to talk about today. Thank you for coming.
One quick question, if you have, please come to the microphone. No.
think you had a slide of it, but just to check. So there is no hope to do it based on standard extraction. What is the status? If you put like instead of H some kind of
No,
fancy extractor?
it's just barrier. We didn't prove any impossibility result respect to extractor. So it's still possible, but to do it, you need the only thing we know is about the impossibility. So you either maybe remove the deterministic. You need a randomized encryption scheme to do it, or you need some computational assumption, but that's still possible. Yes. Right. Thanks.
All right, let's have the next time speak again. Coffee break.
Really nice stuff. Yeah, that's fascinating stuff.
Yeah, thank you.